May 18th, 1941, Lockheed Air Terminal, Burbank, California. The YP-38 climbed through 28,000 feet when Major Signa Gilkey pushed the control yoke forward. He had orders to test the Lightning's high-speed dive characteristics, to find out what happened when America's newest fighter approached speeds no production aircraft had ever reached. At 30,000 feet, Gilkey rolled the twin-boom fighter nose down and let gravity do its work. The airspeed indicator climbed past 280 miles per hour, then 300. At 320 miles per hour indicated, the tail began to shake. Not the gentle buffet pilots knew from stalls or rough air, but a violent vibration that rattled the entire airframe. Then the nose tucked under. Hard. The dive steepened from 45 degrees to nearly vertical. Gilkey pulled back on the yoke. Nothing. The elevators had lost effectiveness. The control surfaces that should have lifted the nose simply stopped responding. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The Lightning was locked in a death dive, accelerating toward the desert floor at a rate that would have torn the wings off any other fighter in the Army Air Corps inventory. What neither Gilkey nor the Lockheed engineers watching from the ground fully understood in that moment was that the P-38 had just encountered a phenomenon that would claim the lives of test pilots, confound the best aeronautical minds in America, and render one of the war's longest-range fighters tactically limited until engineers developed a solution 3 years later. The story of how Lockheed's engineers solved the compressibility problem is not merely a technical tale of aerodynamic innovation. It is a narrative of pilots dying in unrecoverable dives, of German fighter pilots exploiting a lethal weakness they discovered through combat experience, and of a small set of electrically actuated dive flaps that would transform the P-38 from a fighter that couldn't safely dive past 20,000 feet into an aircraft that could outdive every German fighter in the sky. The mathematics of high-speed flight were being written not in wind tunnels, but in the terrifying experience of pilots who pushed their aircraft into velocity ranges where the laws of subsonic aerodynamics simply stopped working. The path to that vertical dive began 4 years earlier in a conference room at Wright Field, Ohio. On February 9, 1937, the Army Air Corps issued a specification for an interceptor unlike anything America had ever built. Requirement X-609 called for an aircraft capable of 360 miles per hour at altitude, able to reach 20,000 feet in 6 minutes, with an endurance of 1 hour at full throttle. The specification demanded performance that exceeded every fighter, then in service by margins that seemed impossible. Lockheed Aircraft Corporation had never built a fighter. The company's reputation rested on elegant commercial transports like the Model 14 Electra, but Chief Engineer Hall Hibbard and his assistant, a brilliant 27-year-old engineer named Clarence Kelly Johnson, saw in the specification an opportunity to revolutionize fighter design. Their proposal, submitted in June 1937, abandoned every conventional assumption about what a fighter should look like. Instead of a single engine mounted in the fuselage, Johnson proposed 2 Allison V-17, 10 engines mounted in twin booms extending back from the wing. The pilot would sit in a central nacelle between the booms. The armament, a battery of machine guns and a cannon, would fire from the nose, providing unprecedented accuracy through centerline mounting. The twin-boom configuration served a specific purpose. The Allison engines would be turbocharged for high-altitude performance, and the turbochargers required complex ducting for exhaust gases and intercoolers to cool the compressed air. Mounting everything in the booms simplified the design and provided space for the tricycle landing gear that Johnson insisted would improve ground handling. On June 23, 1937, the Army Air Corps awarded Lockheed a contract for one prototype, designated XP-38. The contract price was $163,000. Construction began immediately at Lockheed's facility in Burbank. The prototype emerged from the factory on December 31, 1938, painted in polished aluminum that gleamed under the California sun. Test pilot Lieutenant Benjamin Kelsey first flew the XP-38 on January 27, 1939. The aircraft performed beyond expectations. Speed trials showed the prototype reaching 413 miles per hour at 20,000 feet, faster than any American fighter and faster than most fighters anywhere in the world. Rate of climb exceeded specifications. The turbocharged Allisons delivered full power at altitudes where other engines gasped for oxygen. On February 11, 1939, Gilkey took off from March Field in California on a transcontinental speed dash designed to demonstrate the Lightning's capabilities to Army brass and generate publicity for Lockheed. The flight plan called for refueling stops at Amarillo, Texas and Dayton, Ohio, before arriving at Mitchell Field on Long Island. The goal was to break Howard Hughes's transcontinental speed record of 7 hours 28 minutes. Everything went smoothly until the final approach to Mitchell Field. As Gilkey descended through 3,000 feet, both engines quit. He had run the internal fuel tanks dry while attempting to switch to reserve tanks. Without power, Gilkey had no option but to make an emergency landing on a golf course. The P-38 touched down, rolled across the fairway, and struck a sand trap. The impact tore off the landing gear. The prototype slid to a stop in a crumpled heap. Gilkey walked away without serious injury, but the only P-38 was destroyed. The crash investigation revealed no design flaw. Gilkey had simply forgotten to switch fuel tanks during the high workload approach. But the loss of the prototype meant Lockheed would have to proceed directly to the service test YP-38 models without the additional development time the prototype would have provided. The Army Air Corps had already placed orders for 13 YP-38 service test aircraft on April 27, 1939, before the prototype crashed. These aircraft incorporated numerous improvements over the prototype. The engines rotated in opposite directions, with the propellers turning upward toward the cockpit rather than downward. This change eliminated the torque effects that had made the prototype difficult to handle during takeoff. The first YP-38 flew in September 1940. Production proceeded slowly. Lockheed was learning to build fighters, and the YP-38s required extensive hand-fitting and adjustment. By June 1941, all 13 service test aircraft had been delivered to the Army. They were used for evaluation, training, and testing. What the test pilots discovered during those evaluation flights would prove far more troubling than Gilkey's fuel management error. The Army pilots testing the YP-38s reported that the aircraft handled beautifully at normal speeds. Controls were light and responsive. The view from the cockpit was excellent, with the pilot sitting high in the central nacelle between the twin booms. Rate of roll was adequate. The concentrated nose armament promised devastating firepower. The twin engines provided a safety margin over hostile territory. But when pilots pushed the Lightning into high-speed dives, something went terribly wrong. The first indication would be vibration in the tail. Not severe at first, just a buzz that pilots could feel through the control column. Then, as speed increased, the vibration would intensify into violent shaking that rattled the entire airframe. Pilots described feeling like the aircraft was tearing itself apart. Then came the nose tuck. The aircraft would pitch nose down despite the pilot's efforts to maintain dive angle. The dive would steepen from 45 degrees to 60 degrees, then 70 degrees, approaching vertical. Pilots would pull back on the control yoke with both hands, using maximum effort. The elevators would not respond. The control surfaces designed to change the aircraft's pitch had simply stopped working. The Lightning would continue its vertical plunge, accelerating past 400 miles per hour, past 450, approaching 500 miles per hour. At those speeds, the airframe was approaching its structural limits. If a pilot pulled too hard on the controls attempting to force a recovery, he risked overstressing the tail and causing structural failure. If he didn't pull at all, he would simply fly into the ground at terminal velocity. The only solution, pilots discovered, was to ride out the dive. Keep the aircraft pointed straight down. Don't try to turn. Don't try to pull out. Just wait. As the P-38 descended into denser air below 15,000 feet, the controls would gradually begin responding again. The elevator would start to bite. The pilot could then pull back gently, using elevator trim to assist, and recover from the dive with thousands of feet to spare if he had started high enough. But if a pilot entered the dive below 25,000 feet, there might not be enough altitude to complete the recovery. Several test pilots had close calls. Some reported recovering with less than 2,000 feet of altitude remaining. The margins were terrifyingly small. For Major Signa Gilkey, flying that test mission in May 1941, the recovery worked exactly as other pilots had described. He rode out the compressibility lockup, waited for denser air, used elevator trim to assist recovery, and pulled out safely at low altitude. When he landed and reported his experience to Lockheed engineers, the message was clear. The P-38 had a potentially fatal limitation. The Army desperately needed to understand what was causing the problem and how to fix it. But in May 1941, with war spreading across Europe and Asia, Lockheed had more urgent priorities. Production orders for P-38 fighters were flooding in from the Army Air Forces and foreign governments. The British had ordered hundreds. The Army wanted thousands. Kelly Johnson and his team of engineers understood they were facing something fundamental. The tail wasn't suffering from flutter, the resonant vibration that had plagued other aircraft designs. Lockheed proved this by reinforcing the tail structure with thicker aluminum skin. The reinforcement made no difference. The vibration continued unchanged. The nose tuck persisted regardless of tail stiffness. Johnson suspected the problem was related to compressibility, the strange aerodynamic effects that occurred when air flowing over portions of the wing approached the speed of sound. But in 1941, compressibility was poorly understood even by the best aerodynamicists in the world. The phenomenon occurred when local airflow over the wing's upper surface accelerated to velocities faster than the aircraft's forward speed. As that local airflow approached, Mach 1 shock waves would form. The shock waves would change the pressure distribution over the wing. The center of pressure would shift aft, from about 25% of the chord to about 50%. This shift would create a strong nose-down pitching moment. Simultaneously, the shock waves would cause boundary layer separation, reducing the downwash of air flowing over the horizontal stabilizer and elevators. With reduced downwash, the elevators lost effectiveness. The combination of increased nose-down moment and reduced elevator authority created an unrecoverable dive. The faster the aircraft went, the stronger these effects became. The pilot was trapped in a feedback loop where increasing speed made recovery harder, and the nose-down pitch increased speed. Only descending into denser air, where the speed of sound was higher and the aircraft's velocity relative to the local speed of sound decreased, would break the cycle. Understanding the problem was one thing, solving it was entirely different. Lockheed requested time in the high-speed wind tunnels operated by the National Advisory Committee for Aeronautics at their Ames laboratory in California, but NACA was reluctant to test models at velocities approaching Mach 1. The wind tunnel operators feared damaging their expensive facilities. They delayed and made excuses. Johnson pushed harder. He wrote letters. He made phone calls. He traveled to Ames personally to plead his case. Finally, in October 1942, 17 months after Major Gilkey's near-death experience, NACA agreed to test a scale model P-38 in their high-speed wind tunnel. The tests confirmed Johnson's theory. As the model approached Mach 0.68, shock waves formed over the wing. The center of pressure shifted aft. The horizontal stabilizer entered disturbed air. Everything matched what pilots were experiencing. But wind tunnel tests didn't provide a solution. Johnson and his engineers tried multiple approaches. They experimented with different tail configurations, raising the horizontal stabilizer higher above the wing's turbulent wake. They tested various mass balance configurations on the elevators. They tried adding fillets where the central nacelle joined the wing to smooth airflow. Nothing worked. In November 1941, Lockheed tried a different approach. They installed servo tabs on the elevators of YP-38 No. 1. These spring-loaded tabs were designed to provide mechanical advantage when control forces exceeded 30 pounds. In theory, the tabs would multiply the pilot's effort allowing recovery from high-speed dives even when normal elevator effectiveness was degraded. Test pilot Ralph Verdun, age 43, was assigned to evaluate the servo tabs. On November 4, 1941, Verdun took off in YP-38 No. 1 with explicit instructions. He was to test the servo tabs at high altitude, where compressibility effects were less severe. He was specifically warned not to perform high-speed maneuvers at low altitude, where the servo tabs could generate excessive control forces and overstress the airframe. A note was taped to the instrument panel emphasizing this restriction. Verdun completed the high-altitude test sequence successfully. The servo tabs appeared to work as designed. He radioed that he was returning to base. 15 minutes later, witnesses on the ground saw YP-38 No. 1 in a steep dive, followed by a violent high-G pullout. The tail section failed at approximately 3,000 feet. The aircraft disintegrated. Ralph Verdun was killed instantly. The accident investigation revealed that Verdun had ignored the altitude restriction. He had performed a high-speed dive at low altitude, where the servo tabs generated forces that exceeded the tail's structural limits. The servo tabs had worked too well, providing enough mechanical advantage to literally tear the aircraft apart. Kelly Johnson was devastated. He wrote later that he broke an ulcer, worrying about the compressibility problem. The servo tab approach was abandoned immediately. Lockheed engineers went back to studying the wind tunnel data. Meanwhile, P-38s were entering combat with a limitation that every pilot understood. You could dive on the enemy. But you had to start high enough, and you had to avoid steep dive angles. If a German pilot split-said and dove for the deck, you couldn't follow. The compressibility limitation was now a tactical weakness that enemy pilots would learn to exploit. By mid-1942, P-38s were flying combat missions in North Africa, the Aleutian Islands, and the Southwest Pacific. Pilots reported mixed results. The Lightning's range and high-altitude performance were unmatched. The centerline armament delivered devastating firepower. But German fighter pilots quickly learned that P-38s wouldn't follow them into steep dives. A Fw-190 pilot under attack by a Lightning could simply roll inverted, pull through, and dive vertically for the ground. The Fw-190 could safely dive to 450 miles per hour and recover without difficulty. The P-38 pilot watching from above had two choices: follow the dive and risk compressibility lockup, or let the enemy escape. Most chose survival over pursuit. The tactical impact was significant. The P-38 couldn't use the boom and zoom tactics that other American fighters employed so successfully. The Republic P-47 Thunderbolt could dive at speeds exceeding 500 miles per hour and recover reliably. The P-38 couldn't match that capability. German pilots knew it. They exploited it consistently. Throughout 1942 and into 1943, Kelly Johnson and his team continued searching for a solution. They tried dozens of modifications. They tested different wing fillets. They experimented with various horizontal stabilizer positions. They analyzed data from wind tunnel tests and combat reports. Nothing provided the breakthrough they needed. The P-38 would remain in production, would serve throughout the war, but would always carry this limitation. Then, in early 1943, Johnson had an idea. Instead of trying to prevent the compressibility effects, what if they could counteract them? The problem was that shock waves formed over the wing shifted the center of pressure aft. What if they could install devices that shifted the center of pressure forward, offsetting the rearward shift caused by compressibility? The solution was dive flaps. Not the large dive brakes used on dedicated dive bombers like the Douglas SBD Dauntless. Those slowed the aircraft to allow longer aiming time and lower release altitudes. Johnson's dive flaps would be small surfaces mounted on the underside of the wing, just outboard of the engines. When deployed, they would extend downward and create additional lift forward of the center of pressure. This forward lift would generate a nose-up pitching moment that would counteract the nose-down moment from compressibility. The flaps would be electrically actuated, deploying in approximately 1.5 seconds. Pilots would activate them before entering a high-speed dive. With the flaps extended, the shift in center of pressure would be delayed to higher speeds. The elevators would retain effectiveness longer. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Recovery from steep dives would become possible even at speeds approaching 600 miles per hour indicated. Lockheed built a prototype set of dive flaps and installed them on a P-38J model in late 1943. Test pilots flew the modified aircraft through increasingly aggressive dive profiles. The results exceeded expectations. With dive flaps deployed, pilots could safely dive at angles up to 60 degrees from altitudes exceeding 30,000 feet. The nose tuck was greatly reduced. The elevators remained responsive. Recovery was smooth and predictable. One test pilot reported achieving an indicated airspeed of almost 600 miles per hour in a dive, though compressibility error meant the true airspeed was somewhat lower. Regardless of the exact number, the improvement was dramatic. The dive flaps worked. Now Lockheed needed to get them to operational units as quickly as possible. But production and distribution of a modification kit to units scattered across multiple theaters would prove nearly as challenging as solving the technical problem itself. By late 1943, Lockheed had assembled several hundred dive flap modification kits. These kits contained the flap assemblies, electric actuators, wiring, switches, and installation instructions. The plan was to ship kits to P-38 units in North Africa, Europe, and the Pacific. Field maintenance crews would install the modifications, transforming existing aircraft into -J-10 and -J-20 models with full dive flap capability. The kits began shipping in December 1943 and January 1944. Some reached their destinations. P-38 units in the Mediterranean theater received kits and began installations. Pilots who flew the modified aircraft reported enthusiastically about the improvement. They could now dive on German fighters with confidence. The tactical playing field had shifted, but the European theatre of operations faced delays. 200 dive flap kits designated for 8th Air Force P-38 units in England were loaded aboard a Douglas C-54 Skymaster transport on March 3, 1944. The transport, a four-engine cargo aircraft based on the DC-4 commercial airliner, departed from an airfield in the United States bound for England via the Northern Ferry route. On March 16, 1944, as the C-54 approached the British Isles, a Royal Air Force fighter pilot spotted the transport at distance. The silhouette was unfamiliar. The pilot thought he was looking at a German Focke-Wulf 200 Condor, a four-engine long-range reconnaissance bomber. The C-54 and Fw-200 had broadly similar configurations when viewed from certain 15 angles. Both were low-wing monoplanes with four engines. The RAF pilot attacked. His cannon fire tore through the C-54's fuselage and wing structure. The transport went down over the ocean. All crew members were killed. The cargo, including 200 dive flap modification kits, sank to the bottom of the Atlantic. The loss meant that 8th Air Force P-38 units would not receive dive flaps through field modification. They would have to wait for factory-fresh aircraft with dive flaps installed on the production line. The irony was bitter. Lockheed test pilot Tony Levere was in England during March 1944, conducting a 4-month morale-boosting tour of P-38 bases. He flew a specially modified P-38J-25 named Snafuperman that incorporated full dive flap capability along with hydraulically boosted ailerons and other improvements. Levere demonstrated the aircraft's capabilities to pilots who were still flying earlier models without dive flaps. He would climb to altitude, roll inverted, and dive nearly vertically, pulling out smoothly at low level with the dive flaps doing their job perfectly. The pilots watching from the ground could see what they were missing. They wanted those dive flaps desperately, and the kits that would have given them dive flaps were sitting on the ocean floor, destroyed in a friendly fire incident caused by misidentification. Back in Burbank, Lockheed was working to incorporate dive flaps into the production line. The process was complicated. Aircraft coming off the assembly line in spring 1944 were towed outside to the ramp and modified in the open air. Workers would jack up the aircraft, remove access panels, install the dive flap assemblies, run wiring, test the systems, and sign off on the modification. It was time-consuming and inefficient. Finally, in June 1944, dive flaps were integrated into the standard production sequence. The final 210 P-38J models, designated P-38J-25-LO, rolled off the assembly line with dive flaps installed as original equipment. These aircraft represented the definitive Lightning configuration. They included not just dive flaps, but also hydraulically boosted ailerons that dramatically improved roll rate. The P-38, J-25 and subsequent P-38L models were the aircraft Kelly Johnson had envisioned from the start. Fast, long-ranged, heavily armed, and now capable of high-speed dives that German fighters couldn't match. But they arrived too late to save the Lightning's reputation in the European theatre. By summer 1944, most 8th Air Force P-38 groups were transitioning to the North American P-51 Mustang. The Mustang offered comparable range with better high-altitude performance, simpler maintenance, and lower cost. The P-38's moment in Europe had passed, but in the Pacific and Mediterranean theatres, where the improved J and L models served from mid-1944 through war's end, the dive flaps made an enormous difference. German pilots in the Mediterranean theatre, who had grown accustomed to escaping P-38s through steep dives, suddenly found themselves being followed. Luftwaffe after-action reports from summer and fall 1944 include increasingly frequent mentions of P-38s, matching German dive performance. Pilots who had relied on the split-S escape maneuver discovered it no longer worked. Horst Petschler, a Luftwaffe pilot with Jagdgeschwader 3 who survived the war, later recalled encounters with late-model Lightnings. He described how earlier in the war his unit had been briefed that P-38s could not follow steep dives. This weakness was standard tactical knowledge, but beginning in mid-1944, Petschler noticed that some Lightnings were diving more aggressively and recovering at lower altitudes than had been possible before. German intelligence eventually identified the dive flaps through examination of captured aircraft and pilot debriefings. The reports noted that late-model P-38s with distinctive underwing fairings could safely execute near-vertical dives from high altitude. The tactical advice to German pilots was updated accordingly. The split-S was no longer a reliable escape maneuver against these modified Lightnings. In the Pacific theater, where the P-38 dominated American fighter operations throughout the war, dive flaps arrived in late 1944 and early 1945. Japanese fighter pilots had never relied heavily on diving escape tactics the way Germans had. Japanese fighters like the Mitsubishi A6M0 emphasized maneuverability over speed. They couldn't outdive a P-38 even before dive flaps were installed. But the dive flaps still provided benefits in the Pacific. They allowed P-38 pilots to dive steeply on Japanese ground targets during strafing runs, then pull up sharply before encountering anti-aircraft fire. They enabled more aggressive intercepts of Japanese bombers at high altitude. They gave pilots confidence that if they needed to dive away from trouble, they could do so without fear of compressibility lockup. Major Richard Bong, America's top-scoring ace with 40 victories, flew P-38s exclusively in the Pacific. He achieved his final victories in late 1944 flying P-38L models with dive flaps. While Bong's tactical style emphasized surprise attacks from superior altitude rather than prolonged dogfighting, the dive flaps gave him additional options during combat. He could dive more steeply on targets and recover more quickly for follow-up attacks. The technical achievement represented by the dive flaps deserves emphasis. The flaps themselves were relatively simple devices. Each flap was approximately 3 feet wide and extended roughly 18 inches when deployed. They were mounted on the underside of the wing, just outboard of the engine nacelles, positioned to affect airflow over approximately 40% of the wingspan. The flaps created what aerodynamicists call a redistribution of lift. When deployed, they generated additional lift forward of the wing's quarter chord line. This forward lift created a nose-up pitching moment. The magnitude of this moment increased with airspeed, providing more nose-up force exactly when the compressibility-induced nose-down moment was strongest. The result was that the center of pressure remained closer to its normal position even as shock waves formed over the wing. The elevator remained effective at higher speeds. Pilots could control the aircraft through the transonic regime that had previously been unrecoverable. The dive flaps didn't prevent compressibility effects from occurring. They counteracted those effects through aerodynamic compensation. What made the solution elegant was that it required minimal changes to the basic airframe. The wing structure didn't need to be redesigned. The flight control system remained unchanged. The dive flaps were literally bolted onto existing wing structure, with only electrical wiring and switches needing to be added. This simplicity meant the modification could be retrofitted to older aircraft in the field, though the C-54 incident prevented widespread field modification in Europe. The dive flaps also introduced operational considerations that pilots had to learn. The flaps needed to be deployed before entering the dive, not during. A pilot who waited until experiencing compressibility symptoms before activating the flaps would likely find himself already locked in an unrecoverable condition. Proper technique required anticipating the need for flaps based on altitude, airspeed, and dive angle. Pilots were briefed to extend dive flaps any time they planned to dive steeper than 45 degrees from altitudes above 25,000 feet. In practice, most pilots developed a habit of extending the flaps any time they anticipated high-speed maneuvering. The flaps created minimal drag when deployed, so there was little penalty for extending them early as a precautionary measure. Recovery technique also changed with dive flaps. Earlier, P-38 pilots had learned to ride out compressibility lockup and wait for denser air at lower altitude. With dive flaps, pilots could pull out at higher altitudes using normal elevator inputs. This earlier recovery meant less altitude lost during the maneuver and quicker return to fighting altitude. The strategic impact of the dive flaps extended beyond individual combat encounters. The P-38's inability to dive effectively had been a serious limitation that affected mission planning and tactical employment. With that limitation removed, the Lightning became a more versatile fighter. Commanders could assign P-38s to missions requiring aggressive diving attacks without worrying about compressibility restrictions. The development of dive flaps also contributed to broader understanding of high-speed aerodynamics. The wind tunnel testing, flight trials, and operational experience with the P-38 provided data that informed design of subsequent aircraft. The North American P-51 Mustang, which began encountering similar compressibility effects as speeds increased, benefited from lessons learned on the Lightning program. Later jet fighters would face even more severe compressibility challenges as they approached and exceeded the speed of sound. The knowledge gained from solving the P-38's problems helped engineers understand what would happen when aircraft flew through the transonic regime. The dive flaps themselves, as a concept, influenced design of other high-speed features like wing fences, saw-toothed leading edges, and vortex generators that would appear on jet fighters in the 1950s and 60s. The human cost of the P-38's compressibility problems will never be fully known. Ralph Virden's death in November 1941 was officially attributed to structural failure during high-G pullout, but the underlying cause was the compressibility problem that necessitated dangerous test flying. Other test pilots had close calls. Some operational pilots died in compressibility-related accidents, though exact numbers are difficult to determine from accident reports that often listed causes as pilot error or unknown factors. What is certain is that the P-38's tactical effectiveness was diminished for 3 years by a problem that Lockheed engineers identified in May 1941, but couldn't solve until late 1943. Those 3 years represented the critical period of the air war over Europe, when the 8th Air Force was fighting desperately to establish air superiority over Germany. The P-38 units in Europe during that period flew with a handicap that German pilots learned to exploit. The friendly fire incident that destroyed 200 dive flap kits in March 1944 compounded the problem. Had those kits reached England and been installed during spring 1944, 8th Air Force P-38 units might have achieved better results during the crucial months leading up to D-Day. Instead, they continued flying aircraft with compressibility limitations while waiting for factory-fresh J-25 models that didn't arrive in significant numbers until after most units had already transitioned to Mustangs. By contrast, P-38 units in the Mediterranean and Pacific theaters received dive flap-equipped aircraft during the critical final year of the war. The 15th Air Force Lightning groups escorting bombers over Austria, Romania, and southern Germany flew J-25 and L models with full dive flap capability. They achieved solid results against the Luftwaffe during the period from summer 1944 through May 1945. In the Pacific, the 13th and 5th Air Forces flew dive flap-equipped Lightnings against Japanese forces from late 1944 through August 1945. The improved dive performance allowed P-38 pilots to intercept Japanese aircraft more aggressively and strafe ground targets with greater confidence. The Lightning remained the dominant American fighter in the Pacific through war's end, destroying more Japanese aircraft than any other USAAF fighter type. The final statistics demonstrate the P-38's success once the compressibility problem was solved. From mid-1944 through August 1945, P-38 units equipped with dive flaps achieved kill ratios comparable to or better than other American fighters in similar roles. The tactical limitation that had plagued the type for 3 years was finally eliminated. Kelly Johnson later reflected on the compressibility challenge in his autobiography. He wrote that the P-38 flew into a speed range where nobody had been before, encountering fundamental physical problems that weren't understood at the time. He described breaking an ulcer over the issue and working throughout the war to solve it. The solution, when finally implemented, added only minimal weight and complexity while transforming the aircraft's capabilities. The dive flaps represented one of the most successful aerodynamic fixes applied to any World War II fighter. Unlike modifications that required extensive redesign or manufacturing changes, the dive flaps were remarkably simple. Small surfaces, electrically actuated, bolted onto existing structure, yet their impact was transformative. They turned a fighter with a potentially fatal limitation into an aircraft that could safely operate at the edge of the transonic envelope. The lesson extended beyond the specific case of the P-38. It demonstrated that complex aerodynamic problems could sometimes be solved through clever application of basic principles rather than wholesale redesign. Johnson and his team didn't try to prevent compressibility effects from occurring. They accepted that shock waves would form and the center of pressure would shift. They simply added a counteracting force that neutralized the shift's effects. This approach, counteracting problems rather than eliminating their causes, would become a recurring theme in high-speed aircraft design. When jets began encountering control problems at transonic speeds in the late 1940s, engineers applied similar thinking. Wing fences, boundary layer fences, vortex generators, and other devices didn't prevent shock wave formation. They managed the effects of shock waves to maintain controllability. The P-38's dive flaps were pioneers in this design philosophy. They proved that seemingly intractable aerodynamic problems could be solved with relatively simple modifications if engineers understood the underlying physics and thought creatively about solutions. The 3-year delay between identifying the problem and implementing the solution reflected not a failure of engineering, but the genuine difficulty of understanding phenomena that occurred at velocities where conventional aerodynamic theory broke down. The compressibility problem also highlighted the importance of high-speed wind tunnels for aircraft development. Lockheed's repeated requests for wind tunnel time at NACA facilities, initially denied due to concerns about damaging the tunnels, eventually led to the testing that confirmed the source of the problem. Had high-speed wind tunnel testing been available earlier, the COPIS problem might have been identified and solved during the prototype phase, rather than after hundreds of P-38s were already in service. This experience influenced post-war decisions about aeronautical research facilities. The need for extensive high-speed and supersonic wind tunnels became obvious as aircraft approached and exceeded the speed of sound. NACA, and later NASA, invested heavily in wind tunnel facilities capable of testing aircraft at transonic and supersonic speeds. These facilities allowed engineers to identify and solve compressibility problems during design rather than after aircraft entered service. The P-38 program also demonstrated the value of systematic flight testing. Major Gilkey's May 1941 test flight, where he deliberately pushed the aircraft into compressibility and successfully recovered, provided crucial data about the problem's characteristics. His decision to ride out the dive rather than bail out gave Lockheed engineers information they needed to understand what was happening. Subsequent test flights, including Ralph Verden's fatal accident, added to the knowledge base even when outcomes were tragic. Modern flight test programs trace their methodical approach directly to lessons learned from cases like the P-38. Test pilots now work with engineers to develop careful test plans that push boundaries incrementally while maintaining safety margins. The days of test pilots simply taking new aircraft up and seeing what happened were ending during World War II, replaced by systematic evaluation programs that the P-38 experience helped define. For the pilots who flew P-38s in combat, the dive flaps represented a fundamental change in how they fought. Lieutenant Colonel Jack Jenkins, who led the 55th Fighter Group's P-38s on the first American fighter mission to Berlin on March 3, 1944, flew early J models without dive flaps. He later flew L models with dive flaps and reported that the difference was extraordinary. With dive flaps, he could use true boom and zoom tactics, diving steeply on enemy fighters and recovering quickly for follow-up attacks. Robin Olds, who would become one of the Air Force's most famous fighter pilots, flew P-38s with the 479th Fighter Group in 1944. He described a close call during a mission where he dove on a German fighter and entered compressibility before realizing his aircraft didn't have dive flaps installed. He managed to recover using elevator trim, but the experience terrified him. When his unit received J-25 models with dive flaps, Olds considered them different aircraft entirely. The transformation in pilot confidence was measurable through mission reports and combat narratives. Early P-38 pilots wrote extensively about the need to avoid steep dives and maintain altitude discipline. Their tactical discussions emphasized never chasing enemy fighters down to low altitude where compressibility risks were highest. After dive flaps arrived, mission reports showed pilots diving more aggressively, recovering at lower altitudes, and engaging enemy fighters in situations they would have avoided previously. This increased confidence translated directly to combat effectiveness. P-38 units equipped with dive flaps achieved higher victory-to-loss ratios than the same units had achieved with earlier models. While multiple factors contributed to this improvement, including pilot experience and declining German fighter quality, the dive flaps' tactical impact was significant. Pilots could fight the way they wanted to fight, rather than working around a fundamental limitation. The Mediterranean theater provided the clearest demonstration of dive flaps' impact. The 1st, 14th, and 82nd Fighter Groups flew P-38s throughout 1944 and into 1945. These units received J-25 and L models with dive flaps during summer 1944. Their victory totals increased noticeably in the months following the arrival of dive flap-equipped aircraft, even as German opposition was generally declining. Specific engagements illustrated the difference. On October 10, 1944, P-38s from the 1st Fighter Group intercepted German fighters attacking bombers over Austria. The American pilots dove from 28,000 feet in near-vertical attacks, destroying multiple enemy aircraft without losing control at high speeds. Mission reports explicitly mentioned that dive flaps allowed recovery techniques that wouldn't have been possible with earlier models. In the Pacific, where Japanese fighters rarely used diving escape tactics, the dive flaps' primary benefit came during ground attack missions. P-38 pilots strafing Japanese airfields, shipping, and installations could dive steeply on targets, attack from higher speeds, and pull up more quickly to avoid anti-aircraft fire. The improved dive and recovery characteristics made the Lightning a more effective fighter bomber, complementing its already superior range and firepower. The technical specifications of the production dive flaps reflected careful engineering optimization. Each flap assembly weighed approximately 45 pounds, including the actuator mechanism and mounting hardware. Total weight penalty for the complete system, including both flaps, wiring, and cockpit controls, was approximately 120 pounds. This represented less than 1% of the P-38's loaded weight, a remarkably small penalty for such significant capability improvement. The dive flaps extended to a maximum angle of approximately 35 degrees below the wing's lower surface. Extension time was 1.5 seconds from initiation to full deployment. Retraction took approximately 2 seconds. The electric motors driving the actuators were powered from the aircraft's 24-volt electrical system and drew modest current during operation. Mechanical stops prevented overextension or asymmetric deployment. Pilot control was through a switch on the throttle quadrant, positioned for easy access during high workload situations. The switch was spring-loaded to return to neutral position after activation, preventing pilots from accidentally leaving flaps extended or retracted. An indicator light on the instrument panel showed when flaps were fully deployed. If electrical power failed, the flaps would retract under aerodynamic loads, defaulting to the safe configuration. The system's reliability proved excellent in service. Maintenance records show few problems with dive flap actuators or associated components. The simplicity of the design, using proven electrical actuators and robust mechanical linkages, meant field maintenance crews could service the system without specialized training or equipment. This reliability was crucial for operational effectiveness, ensuring pilots could depend on the system working when needed. The broader impact on aircraft design extended into the jet age. When the Lockheed P-80 Shooting Star, America's first operational jet fighter, encountered compressibility problems during development in the mid-1940s, engineers applied lessons learned from the P-38. While the P-80's solutions differed in detail, the approach of using small aerodynamic devices to counteract compressibility effects came directly from Lightning experience. The North American F-86 Sabre, which would achieve success in Korea using transonic diving attacks, incorporated dive recovery features informed by P-38 development. The Republic F-84 Thunderjet, successor to the P-47, included compressibility management features. From its initial design rather than adding them after encountering problems in service. The P-38's difficult path had made the route easier for aircraft that followed. By war's end, in August 1945, Lockheed had produced 10,038 P-38s, including reconnaissance variants. Approximately half featured dive flaps installed either at the factory or through field modification kits that successfully reached operational units. This meant roughly 5,000 Lightnings served throughout their operational lives with the compressibility limitation that had plagued the design from 1941. The other 5,000, including all L models and late J models, represented the aircraft as Kelly Johnson had intended. Fast, long-ranged, heavily armed, and capable of sustained high-speed flight through the transonic regime. These late-model Lightnings demonstrated what the design could achieve when its fundamental limitation was finally eliminated. They validated Johnson's original concept and proved that the twin-boom configuration could succeed as a fighter. Post-war, many P-38s were sold as surplus or scrapped. Some found civilian uses, others were placed in storage. The type never saw combat again after World War II, unlike other wartime fighters that served in Korea or other conflicts. But the P-38's technical legacy lived on through the lessons its development provided about high-speed flight, compressibility management, and systematic problem-solving in aircraft design. Kelly Johnson would go on to lead Lockheed's Skunk Works, creating revolutionary aircraft including the U-2 reconnaissance plane, the SR-71 Blackbird, and the F-117 stealth fighter. He often cited the P-38 compressibility problem as one of the most challenging technical issues he ever faced. Solving it required patience, systematic testing, creative thinking, and a willingness to try unconventional solutions. These became hallmarks of Johnson's approach throughout his career. The pilots who flew P-38s in combat never forgot the aircraft's distinctive characteristics. The twin-boom configuration made it instantly recognizable. The centerline armament provided unmatched accuracy. The twin engines offered reassurance over hostile territory, and for those lucky enough to fly late models with dive flaps, the ability to dive with confidence made the Lightning a truly formidable fighter. German pilots who survived the war and wrote memoirs consistently mentioned the P-38 as a formidable opponent, particularly late in the war when improved models arrived. They described how earlier Lightnings could be evaded through diving, but later variants matched or exceeded German dive performance. This evolution, from flawed but promising fighter to fully capable combat aircraft, demonstrated what systematic engineering effort could achieve. The story of the P-38 dive flaps is ultimately a story about persistence. 3 years passed between identifying a problem and implementing a solution. During those years, pilots died, aircraft were lost, and combat effectiveness was compromised. But Lockheed engineers never stopped searching for answers. They tested dozens of modifications. They conducted hundreds of wind tunnel runs. They analyzed thousands of data points from test flights and combat reports. When they finally identified the right solution, it was elegantly simple. Small electrically actuated flaps mounted under the wing, creating lift that counteracted compressibility-induced pitch moments. No fundamental redesign required. No major manufacturing changes needed. Just a clever application of basic aerodynamic principles to solve what had seemed like an intractable problem. The lesson transcended aviation. Complex problems sometimes yield to simple solutions if engineers understand the underlying physics and think creatively about interventions. The P-38 couldn't be redesigned from scratch to avoid compressibility, but it could be modified with small devices that managed compressibility's effects. This distinction between preventing problems and counteracting them opened new possibilities for solving difficult technical challenges. For the men who flew P-38s in combat, particularly those who transitioned from early models to late models with dive flaps, the difference was profound. They went from flying an aircraft with a potentially fatal limitation to flying one that could safely operate throughout its performance envelope. The confidence this inspired, the tactical flexibility it enabled, and the combat effectiveness it produced justified every hour spent solving the compressibility problem. The mathematics of transonic flight were being written in wind tunnels and test flights during the early 1940s, explored by aircraft pushing into velocity ranges where aerodynamic rules changed. The P-38 Lightning was among the first to reach those speeds in level flight and in dives. It paid the price for being first, encountering problems nobody fully understood. But it also provided solutions that would benefit every high-speed aircraft that followed. The dive flaps that emerged from 3 years of development represented more than just a fix for one aircraft's problems. They demonstrated engineering principles that would guide transonic and supersonic aircraft design for decades. They showed that systematic testing and analysis could solve seemingly impossible problems. They proved that simple modifications, properly designed and applied, could transform an aircraft's capabilities without wholesale redesign. When the last P-38L rolled off the production line in August 1945, it represented the culmination of 8 years of development from the original 1937 specification. The aircraft that emerged bore Kelly Johnson's distinctive twin-boom design, but it had evolved far beyond the prototype that crashed on a golf course in 1939. Most significantly, it incorporated dive flaps that solved the compressibility problem that had limited the type for half its development life. Those final production Lightnings, equipped with dive flaps, hydraulically boosted ailerons, improved engines, and all the refinements accumulated through years of combat experience, represented the P-38 as it should have been from the start. Fast enough to catch anything in the sky, agile enough to fight when necessary, capable of diving at speeds that terrified enemy pilots, and able to recover from those dives safely, every time. That capability, the freedom to dive without fear of compressibility lockup, was what 200 dive flap kits sitting at the bottom of the Atlantic were supposed to provide to 8th Air Force pilots in 1944. It was what Ralph Verdon died testing in November 1941. It was what Major Signa Gilkey survived in May 1941 by riding out an uncontrollable dive and trusting that denser air would eventually restore control. The dive flaps gave P-38 pilots what every fighter pilot needs: confidence in their aircraft's capabilities and trust that the machine will respond when demanded. With that confidence, pilots could fight aggressively, knowing they could recover from any situation. Without it, they had to hold back, always wondering if this dive would be the one they couldn't recover from. German fighter pilots who learned to exploit the P-38's compressibility limitation during 1942 and 43 found their escape tactic neutralized during 1944 and 45. The split S and vertical dive that had reliably worked for years suddenly became dangerous. Lightnings were following them down, matching their dive speeds and firing accurately during the descent. What had been a reliable escape maneuver became a death trap. This reversal, from exploitable weakness to feared capability, demonstrated the impact of solving a fundamental limitation. The P-38 didn't become faster or more heavily armed when dive flaps were added. Its basic performance envelope remained unchanged, but the ability to operate confidently throughout that envelope, particularly at the high-speed extreme, transformed tactical effectiveness in ways that raw performance numbers couldn't capture. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.